Alrighty, so we are live. Today, we'll be listening about performance features in C#, and this will be presented by Jared Parsons. So Jared is the developer lead for C# compiler team and a member of the C# language design team. So if you have any questions C# related, that's the person. He has a strong passion for developer tools, open source, and infrastructure. And I just checked the number of his pull request to Roslyn repository, and it's 779. So that's the person if you want to listen to about C# and all the features inside of it. So without further ado, let's move on to the presentation.
Awesome. All right. So thanks for coming to my talk about performance features in C#. As was mentioned, my name is Jared Parsons. I'm the C# compiler lead, as well as a member of the C# language design team. Overall, I've been working in .NET language space for about 15 years now. So this is an area I'm particularly passionate about and really happy to be here giving a talk on. So I want to kind of start this off and kind of set the stage for the history of kind of performance in C# and how that lines up with all the work we've been doing recently in .NET Core, and kind of setting the stage for how we got there and why the inspiration for some of the changes we've been making. Now, there are a couple of key traits that'll be a part of every performance feature that we do in C#. They're going to be attacking one or more of the following things. They're going to be giving developers the tools to reduce heap allocations, removing unnecessary copies, because a lot of reducing heap allocations involves moving classes strategically to structs, and that can change the copy semantics of your code from a simple reference type to a series of values. And giving developers the tools to control that can be really beneficial in some low-level scenarios, as well as giving developers the tools to reduce CLR overhead. .NET is a type and memory-safe environment, and that has tremendous benefits to programmers, but it also has costs. The CLR adds items like bounds checking and force zero. And this is another aspect that you might want to be able to control a little bit better in your performance sensitive areas. Now, one thing I think gets kind of lost to history is that C# is a language that was designed with performance in mind, especially compared to contemporary languages like Java. Like right out of the gate, we had features like structs, an entire kind of type which defaults to stack allocation over a heap. We had ref parameters, which let you control the costs and semantics of how those structs were passed between methods. And we also had unsafe, which is kind of like the skeleton key of performance in kind of C# too. It allowed you to return, by pointer, take things by pointer, which was very efficient. You could return interior pointers, and you could do pointer arithmetic and other tricks to avoid all kinds of kind of CLR overhead. And then 2.0, we added generics, which was, once again, removing a lot of kind of overhead and collections APIs, removing boxing on the way in and casting type checking on the way out. And these features really carried the language for a long time. In C# 3 through 6, though, there was a bigger focus on productivity. And a lot of that had to do with the fact that the .NET framework had moved to be a part of the operating system. And that meant that every time we made a change to the framework, it basically shipped to every Windows customer on Patch Tuesday. And that meant that it kind of started making it harder and harder to innovate in the runtime, because every change was essentially forced onto customers, and that caused breaks and disruption. And that meant for a long time, the language was we didn't have any new opcodes. We had very little opportunity to kind of work with the runtime team. And hence, for a long time, we kind of shifted the focus into productivity land. But then lately, you've probably noticed there's been a surge of performance features, and we're going to talk about a lot of them here. And the reason for that is a couple of things. One was the move to .NET Core, because this fundamentally changed the acquisition model of the framework to be completely customer controlled. Customers make the decision when they move from .NET 3 to .NET 5 to .NET 6, and so they are in control of when they move and how they react to any kind of behavior changes we've introduced between the versions. There's also a dedicated focus on performance, particularly web-based scenarios, where we want to make the platform faster startup, smaller footprint, and lower latency. And about the same time we moved to .NET Core, the Midori project was ending. And that was a research project that was really focused on C# and .NET innovation, particularly in the area of performance. And many of the features we're going to talk about here kind of had their incubation history in that project. And many of these team members ended up moving back to .NET at this time. And overall, on the language side, we had a bit of a mentality shift on how we thought about performance features. For a long, like one of the big conversations we have when we talk about a feature in C#, a potential one that we're looking at, is how many developers are going to use this? Particularly, and that's really important, when you're talking about productivity features, you want to make sure you're getting the bang for your buck. You're using a feature that a lot of people are going to use to make their apps more productive. But with performance features, though, it was always at a bit of a, kind of an uphill battle, because performance features tend to be used by the minority of developers. But when we kind of step back and look at the space, if you look at like a customer application, like a 10,000 line or 50,000 line customer application, you might say, wow, that's a big application and we should help them write it better. But under the hood and the platform that they're running on, when you think about the libraries they're consuming, the BCL and the .NET runtime, there are millions and millions of lines of code underpinning even the simplest applications. And the minority of developers are the ones who write that platform that all the other applications run on. And so we began to think of performance feature in that perspective. Essentially, like this is a quote kind of that taken from those debates that really kind of represent the mentality shift we had, which is, yes, that performance feature, it's only going to be used by 1% of developers out there. But that 1% writes 99% of the code that executes in a customer application. And that kind of mentality shift really kind of was the inspiration for a lot of the work that we've been doing in the language over this time. And that really kind of takes us into like the .NET Core era of C#. So like 7 through 10. So about the last 5 years of the language. So in C# 7, you started to see like the kind of fruits of this thinking and overall efforts that we've been working on. This is where we started getting the features for like ref returns, and ref locals, as well as things like value task. And then in 7.2, we added the concepts of read-only to our refs, as well as ref structs, and kind of most importantly, span of T. Now, span of T was a big shift for us because it gave us a type-safe representation of contiguous memory. It is a type that can essentially hold all of the different types of contiguous memory, be it pointers, arrays, or strings. And it does this in a type and memory-safe way that doesn't incur any allocations. And this allowed it to become the foundation of our high-performance APIs. And we're going to kind of take a quick look at how APIs were able to evolve from kind of the C# 6 days to C# 7 as we introduced all of these new features. Now, the first one we're going to look at is kind of the work we did with span of T. So to do with that, we are going to take a look at this little API here, which is a very simple number parsing routine. It takes an array of characters, ASCII characters, and converts them to a number. And up here, you will see that we, pass in an array, and if we parse this out, we're going to get the number 42. But what happens when your customer's data looks more like this, where it is an array, which is a mix of numbers and characters, and you only want to look at a particular portion? Or what if your customer is looking at characters in another form? Perhaps they have a string where they have a number and more data. Or they're in kind of the lower level parts of their code where they are potentially using something more advanced like stack allocations. So here as a library author, when you're kind of looking at the different types of data that your customers have, you have to ask yourself, like, what do I want to support? And particularly, what do I want to support to make sure that my customers can get the maximum performance out of their applications? And in the C# 2 days, you would look at this and you say, like, wow, I can't take an array. I need to take an array which has an index and an length. I need to be able to do the same type of change for strings. And I also, to really satisfy my high perf customers, I'm going to have a pointer version. The next thing you probably did when you looked at this and you said, okay, I have to support all of these different overloads in order to support all of my customers. Now, how am I going to write my code? Because I only want to write my code one time. And so I need to find the overload that all of these other overloads can feed into. And when you look at it, you'd pretty quickly say, like, I have to put my actual algorithms in the unsafe methods of my code, because that is the only overload that all the other ones can feed to. And this is something our customers kept coming back to us and saying, like, if I want to write high performance code in .NET and I pretty much, you force my hand, you push me into a corner where I have to write unsafe code to really satisfy all of the scenarios. And that kind of devalues the platform because .NET's type and memory safe. And we're saying, well, if you want high perf, you really have to go to unsafe over here. But this is where span of T came to the rescue. Because here we could just say, hey, span is the unified representation of all these other forms of memory. So I could put read-only span where I used to have my array because it very much has the look and feel and API of an array. And all of my other overloads could just feed right into that. I can take the data here, I can convert it to a span, I can slice it on the index and length, or I can even pass my pointers through. So I can say, parse a new span of char with pn length. And now I can support my customers. The majority of my code is written in safe now, and it's much easier. Even better, I don't even have to provide these APIs to customers anymore. This extra overhead is unnecessary. I can express my APIs in terms of span and tell my customers, hey, this is a span-based API. You go ahead and do the work to pass the data that is needed. And so this was really foundational for .NET because before span of T, the only option we had for exposing this really high level, these high performance APIs was pointers. And that's not great. Span, though, gave us kind of the building block that we and customers could use to expose these low-level, high-performance APIs. So next thing we're going to take a look at is how ref and read-only were kind of beneficial to the system. So here we have a little document parsing class. And so this takes a byte stream of data. It converts it to a document, which is just made up of a series of sections, and then it passes it to a callback for processing. And you can see here a section is, just a simple data type. It's got a lot of tokens in it that you probably read back from different data storage. And a document is more or less a simple collection type of sections. Now, if we were looking at this from the perspective of performance, and we said, okay, we need to kind of increase the performance of this. One of the low-hanging fruits that you might want to come to, you would say quickly, hey, we're doing a lot of allocations of this section type. Let's make this a struct so that we can just take the GC pressure down on this method significantly. We just now have the array and the document type. And this works, and this will immediately, positively impact the allocations you have in your code. But you've introduced a subtle trade-off here, because now that it's a struct, you're no longer passing a 4 or 8 byte reference around. You're passing a 28 byte bag of longs. And that means this get method is more expensive. These sets and contains are also subtly more expensive. Probably the more impactful ones, though, is get is probably the most likely API to be called in a loop. You've added a lot of copy overhead here. And also subtly in this for each loop, you've added another set of copies, because every time you're for eaching these values, instead of taking a reference out of the array, you're actually taking an entire copy of the values. Now, from the perspective of C# 2 or C# 6, we had a couple of tools in our toolbox we could use. The first is we can say, well, we can fix some of this by just using ref passing. We can get back the performance of passing by just using a ref here. And that works, but it also comes at a cost, because now you've complicated your consuming code. So now when someone wants to call document.contains, they can no longer just use simple expressions, because a ref requires of a local or an array or a field to be passed here. And so this is another case where you had to make a choice between performance. You had to compromise on performance and something else. In this case, it was usability. And that's really unfortunate here. Now, and if we wanted to fix the copies on section here, we could do that. We could do that by saying hey, let's just use pointers. Just take the, use the awesome fixed command. And this would work, provided I actually made this unsafe. But once again, I'm adding more overhead because fixing is not a cost. I'm putting unsafe into my core methods. Worse, though, is when we get to this get method here. Because with the get method, we don't have a lot of options on how to fix this extra copy overhead. We could try to make this a pointer. But that has flaws because our backing data store is an array, and we can't really return a pointer into that array out of this method, because we need in order for that to happen, we need our consumers to fix the array for us and make sure they fix that array for the entire time that the document is being used. In order to do that, we have to start exposing our internals. We probably just end up exposing the array and telling our customers, well, you just do the fixed yourself. And so this is where kind of like with C#6, you started getting stuck. You had to make all these trade-offs with usability when you started pushing on performance. But now with C#7 and beyond, let's look how we can make this nicer. So first off, we can just use ref returns here. In the same way that you can pass parameters by ref, you can now also return values by ref. And you see the change to the code is very simple. I'm just taking a ref out of the array and marking the return as ref. And with this, there's no need to communicate. There's no complication of who is fixing the array. When do the pointers become invalid? The language and runtime work together such that they guarantee this code is going to be type and memory safe. If your code can compile, it will be fine. It will work just as you would like it to. And best is, when you make an API ref returning, it doesn't impact existing call sites. Like people who were using this as a non-ref returning API, they were just reading values out. Their semantics don't change. It just improves the performance for simple items like reads or for people who know to take advantage of it. And even better, in addition to having ref returns and ref parameters, we also added ref locals. So now we can just make this section here in the same way we can turn the ref. We can take a ref to the array as a local. And once again, get this copy semantics back to what they were when we had it as a class. And so now, I mean, this really, with ref returns, ref locals, we kind of completed the picture here. Now we have ref parameters, ref locals, and ref returns. And they all kind of seamlessly integrate into each other. So the next thing we would really like to kind of fix here is the fact that we're taking this section data by ref for contains. But the ref kind of implies something to it, makes our call sites more complicated, but it also implies to our callers that, hey, we might mutate this value. We might assign back into this. So you should be kind of careful about that. And that's not what we're doing here. We are just reading from the values. What we would ideally really like to be able to tell customers is, hey, we're taking this ref, but we're taking it in a read-only fashion. Now, while C# does not allow for that exact syntax, we'd allow for that exact concept with in parameters. And in is literally just a ref read-only. We just made the parameter syntax more readable, give it more synergy. So we had, in, out, ref. It sounds a lot better than read-only ref, out ref. So now this is great because now our API is actually expressing what we wanted to express here. Even better, our call site, the way we used to call the code before we started introducing ref, is the exact same. We can use expressions here again because the compiler, even though under the hood is going to pass by ref, the compiler lets you use expressions, and it just does the heavy lifting of the rewriting for you. Now, this is all well and good, but when we made this read-only, we actually introduced yet another set of copies into our code. And the reason why is that whenever you make a method call onto a struct in a read-only location in C#, the compiler will first make a defensive copy of the struct and then invoke the method. And the reason for that is the compiler just has to assume that every method call can mutate the data in the struct. And so to keep the semantics of read-only what they should be, the compiler has to make a defensive copy to make sure you don't mutate that read-only memory. Well, if you look down here on data, we're invoking a series of properties. Each one of those properties is really just a method call. And so every time for each one of these properties, the compiler is going to copy data as a local, invoke the property, and then it will do it again, and then again. And so that's really kind of unfortunate here. Moving from ref to ref read-only, we ended up actually introducing a lot more copies into our code. The good news is we can continue to use read-only to let the compiler know that these operations are not mutating. We can go up to these properties right here, and we can say, hey, these are all read-only operations. These are operations which are not going to mutate this struct. And when we do that, the compiler is now aware that that's not going to happen. It no longer needs to make defensive copies, and it can invoke them directly on the parameter. Even better, though, we don't have to have the tediousness of iterating every member here. We can actually just go up to the struct itself and say, hey, this is read-only. There's nothing on this struct that's going to mutate, so you don't have to worry about copies for any of the methods here. And that is a fantastic, benefit because the design guidelines are that struct should not be mutating. And by having this declaration syntax, we make it much easier to meet those guidelines. And so this is kind of a tour of like how all of the work we did with ref, like read-only and ref structs can really serve to make code that used to be hard to write in kind of the C#6 days a lot better as you move into like the C#7 and beyond. Now, I know I harped a whole lot on like struct copies there. And I'm sure some people in the audience are like, that's kind of a strange thing to like work, like maybe that's a strange thing to focus on. But it actually adds up very significantly in high performance loops. So what we have here is a benchmark where I essentially took the rough code in that demo, wrote a benchmark.net over it where I returned sections by value, by pointer, and by ref. And you can see that the by ref versus by value is almost 10 times faster in the return method. And it's even faster than pointers. Now, the pointer thing is a little bit gray area because part of the overhead when you deal between pointers and references is the fixed operation and fixing the memory. And where you fix the memory, like where you choose fixing in the loop, out of a loop, can really impact like what your benchmarks are. But then again, it's yet another thing you have to think about when using pointers that you don't have to think about when you're using references. Now, C#8, we didn't have as much in the way of performance. We added the unmanaged constraint. That is one where you can now essentially have a type parameter. You can say it's unmanaged, and that lets you do really awesome things like take pointers to type parameters, if that's something you enjoy doing, as well as adding the kind of the read-only members feature and on top of read-only declarations. In C#8, we were busy with a feature you may have heard of called nullable reference types. It took up just a small amount of our time. Big. But C#9, we kind of really started getting back into like a lot more performance work. And I only have time to go over a few of these today's, mostly function pointers, skip locals, init, and source generators. The other two, module initializer, native integers, definitely worth reading up on in terms of what the benefits they can provide to your programs, but limited time here. So first I want to talk about is skip locals init. So what you're going to see here is a pretty common pattern in .NET, modern .NET code today. I'm doing a read method. I have a span of bytes and an encoding, and I need to kind of temporarily convert them to a character array and process those characters. And because this is a just an artifact of this method, I don't want to do a heap allocation. I don't want to pollute the heap. I know it's going to be kind of a limited size of characters, and I'm going to stack allocate that array. And so this is fantastic, and this works great. It's a great use of stack alloc. Unfortunately, though, part of the requirements of the .NET runtime is that we zero out locals. Well, that stack alloc array represents a local that is 1,024 bytes long. And so the CLR will emit the code to zero out that memory. And that is just not needed here. So in this case, we're allocating a giant array, then we're going to zero it all out, then we're going to write non-zero, we're going to write our bytes to it, and then we're only going to read the sections that we already wrote to. And so that zero in a memory is wasteful. And it's another one of these things that as more and more high performance code starts adopting stack alloc for spans, they start incurring this extra zero memory cost that is adding up in their applications. So we added this feature called skip locals init. And what that does is it gives developers, it causes the C# compiler to not emit the flags, which zeroes out memory. And so you can apply this attributes to methods, types, or assemblies, and it will just completely avoid all the zeroing out here. And you can see this in the ASM of this method. So we have the normal one, which does not have the attribute, and the version with the attribute. And you can see here on the left, missing the attribute, we generate this ASM for essentially running a loop over all of these elements and pushing zero until exhaustion. Whereas in the other one, we just sub the stack, create the memory, and move on to the rest of the application. It's definitely really handy if you're something to look into if you're doing a lot of stack allocations in your programs. So another thing we added was function pointers. And I got to tell you, when we went to C# language design and said, hey, we're going to add function pointers to the language, we think this is a great idea. There may have been some pushback on the function pointers, Jared. You mean that feature from C? You want to put that in C#? And there may have been healthy skepticism as to whether or not this was a good idea. But it turns out, like when you really sit down and look at it, native interop is super common in high performance code. I mean, just think about the BCL. A lot of the BCL is consumed with transitions between kind of our managed code and the .NET runtime, as well as like, anyone who's doing any kind of graphics programming is probably calling into DirectX or some other underlying APIs. People who are wrapping kind of native libraries, like if you're doing any crypto work, you're probably calling into libSSL. And all of this, making those transitions between native and managed memory fast is really important for those low-level APIs and the performance of the platform overall. And when we didn't have function pointers in the language, the only tool in the toolbox that developers had was allocating delegates, doing the work to convert them to a function pointer, and using that in application. And that had a number of downsides, as you can kind of see in this sample here. So at the bottom, we have this API like read on a stream, with a byte PV. How much did we read and where did we read it? It's a very standard native API for reading bytes. But in order to kind of get a function pointer for this, we ended up having to define a delegate type. Can't use function or act because you can't use pointers as type arguments. We had to store that delegate as a static to make sure that it didn't get collected by the GC. Then we had to have the pointer that we pulled out of that delegate. And then typically they all had some lazy reading code associated with them. And if you look at this code, it's cumbersome, it's annoying, it has allocations and overhead, and it also has a race condition inside of it. And so, not great. With function pointers, though, the code is very straightforward. We just function pointers is something that has actually existed in the runtime since 1.0. It's just never been exposed by the C# language. And all we did was essentially expose these underlying primitives by allowing you direct access to like the opcodes that turn method addresses into function pointers. And even better, compared to what we had with delegates, with the new function pointer syntax, you can have managed calling conventions, unmanaged calling conventions. You can have fast calls, cdecls, platform calling conventions. And you can also end up even controlling items like how the GC works, like what GC mode do you transition into when you go from managed to native. And that can be really powerful in some of your low-level code. And this has been a real boon to some of our key libraries. Now, something else we did in C#9 was we added source generators. Now, source generators, what they essentially do is they are giving library authors a hook into the compiler. At compile time, we give you access to the compilation. And libraries can then return and say, I want to add this source code to this application. Now, if you're unfamiliar, compilation is a high-fidelity API into the .NET compiler. It provides access to syntax trees, semantic models, like the access to the references, the options. It allows you to do deep inspection on your customer's code. And it's so powerful, like the Visual Studio experience for C# as well as analyzers are all built on top of these APIs. And this has the potential to provide massive productivity and performance boost to developer code. So we're going to do a bit of a demo. I want to show you a source generator that we are looking to potentially add into .NET 7 around regexes. So here we just have a very simple class for an input regex, which if you can look at this and recognize it, it's basically a lazy man's email regex, compiled ignore case. Now, when you think about a regex and what all this API has to do, when this application is running, the first time I call this isMatch function, the implementation regex, it has to parse this regex out. It has to generate all the IL for recognizing matching input to this particular reg expression because I used compiled. It has to then create an assembly for that and load that assembly into the current runtime. And as you can imagine, that's kind of expensive. It's saying, hey, this API call is going to generate and load an assembly into the runtime. That's expensive. And that does kind of impact startup. And if people with heavy uses of regex, you'll see all kinds of little tricks for how they try to get that cost pushed into different parts of their code. Well, with source generators, we have the opportunity to fix this problem. So let's just say I'm going to define a method called private static regex. Gotta do the partial method here. We're going to find a method here, and we're going to tag it with this attribute called regex generator, and then we're going to yank all that, put it in here. And now what you'll see is What this has done is I've defined a partial method. So this is a method without an implementation that someone else could fill in. I could fill this in somewhere else in my code. But I've added this attribute called regex generator. And what that did is that signaled a source generator that I was running in my application to say, hey, why don't you generate all of that regex code at compile time? And we can actually go and see this. So if we actually open up Solution Explorer, we expand our analyzers nodes, look into our generators, we can actually pull out and see what is going on under the hood here. And you can see, like, I have this partial method, like this code is filling out that partial method we filled out before, and it is filling it out. And this is all the code that it had to generate in order to match this regex. And this code is now, all of that heavy lifting is now being done at compile time, not at runtime. And best, because this is C# code that gets put into your application, it has a number of other tremendous benefits. Like one, if you're running cross-gen on your application, this code now gets cross-gen. If you're doing Pogo optimizations, bam, this is part of your Pogo set. Trimming, this gets included in trimming. If you are debugging your code, I mean, have you ever wanted to debug through a regex and see, like, why is this failing? Why is this not matching? Well, now you can, because a regex actually exists in C#, and you can just step right through this in your debugging code. And what I think is, in some ways, some of the most fun with these is you can actually pull this off to the side here, and you can just start iterating on your regex. So let's get the regex down to nothing, and let's just type out some regexes. And you can just start to watch the code that the regex is generating and start to get a sense for how does it actually match these values. And you can see here that it kind of, for a non-regex, this is really a string match. It's doing exactly what you would expect. It is just making sure a text span has a certain length that's calling to lower in all of these elements and comparing it to the fixed string. But if you wanted to say, like, well, I want it to end with any number of exclamation points, then you can immediately see the change here and how it starts generating loops to start processing those values. And even cooler, you can start to see some of the weird and fun optimizations it does. So as you see here, I have ignore case specified. Let's see what happens when I delete ignore case and just use compile. Notice that it's no longer actually doing string comparisons here. Well, it's doing a string comparison for that second character. But for the first character, it's reading the text stream as an unaligned integer and then saying, well, you know, if it's little endian compared to this number, if it's big endian compared to another number. And these numbers are what represents DO, essentially, when you write them out as integers. And it turns out that this is significantly faster and makes your regex code better. And you can really just start playing around with the regex implementation and just looking at all the cool and neat optimizations that they're doing. But overall, like I said, this is a generator we're looking to add to .NET 7. It was written by Stephen Tobe. There are many other generators out there for, like, JSON serialization. There are helper generators for, like, iNotify property change. They represent an enormous amount of potential into, like, how we can expand the platform and improve it. And it's definitely something to keep track of. Now in C# 10, we made a couple other changes. We had the source generators v2 API. That was much more about taking all the generator work we had done in C# 9 and making it a little more incremental so that it worked a little bit better in Visual Studio and IDE-based scenarios. We also did a lot of work on string interpolation. And so string interpolation is this really handy feature for how you can build up strings. You can just, you have holes that you can fill in with expressions, and the compiler will do the work to make this work with APIs like stream format. So it's a nice, convenient API for building up strings. But the implementation of it leaves a lot wanting, because here you can see the inefficiencies, like the obvious one, like we're allocating an array to pass some parameters. We are then boxing every one of these arguments as we put them into the array. And some of the more subtle cost here is the C# compiler had to parse that format string out. It had to look for all of the holes, pull out the expressions, and then rewrite them as the numeric versions. Well, and it also had to do that if there were format specifiers, which I didn't demo here. Well, string.format also has to do that, but it has to do it at runtime. And so the compiler essentially did all this work to parse out the string, get it all into good format, and it kind of threw it away until the runtime, you can do it again at runtime, have fun. And it turns out this is expensive, and it adds a lot of cost. And what we were finding is a lot of customers were coming back to us and saying, this feature is great, we love it, but we can't use it in anywhere we have like performance sensitive code because the overhead is just too big. Well, in C# 10, the exact same code generates just a little differently. What we've done is we've tried to move all that compile time cost and keep it at compile time. And so what we've done is we've introduced this idea of interpolated string handlers. And these are really builder types where we essentially give them all the information about the string in a builder style fashion where it doesn't require them to do any parsing or any thinking. They just have to respond to a few simple commands, append literals and append format. And you can see right here in the constructor, we're telling this handler, hey, the length of literals I'm going to give you is 3. I'm going to give you 3 string characters as a part of this, and I'm going to give you 4 formatted arguments. And then we just call in order, as it was written down in the string, append format, append literal, over and over again. And at the very end say, now you can give us a string back. And this avoids all the overhead I listed before. There's no boxing here. There are no arrays. All the parsing is done ahead of time. And what's even really cool is this append formatted method. The C# compiler is just doing overload resolution on the handler types. So no matter what the argument types are here, we will pick the best append formatted method that we would append if you just wrote this code out by hand. And this means that handlers can then add overloads for types they have very detailed understanding of how to format better. For instance, the default handler understands how to format spans very well, and so it has a very special handler for that. Now, this API it's actually completely pluggable. You can go to pretty much any API that accepts a string today, and you can put a handler in there for that string and have your own customized implementation. We have ones where the handlers are actually, instead of creating a string, they're writing into a span buffer and returning, and so basically having completely allocation for you, like interpolation, which is really neat. But this is definitely something, it's very pluggable, and I don't have time to demo all the pluggable ways here, but we're something we're really happy with. And when you look at like the performance wins that we're getting out of this is comparing that first sample of a formatting versions just between C# 9 and C# 10. And again, the customer changed nothing. All they did is move from .NET 5 to .NET 6 or C# 9 to C# 10. And you can see here that straight up, it's almost twice this fast in the new code. And we have about a fifth of the allocations. So we have a lot of good data to say this is going to be a big win for a lot of people's applications. Now, that kind of takes us through like where we are today, through kind of what I would call the more modern area of performance in C#, like 7 through 10. But I want to give you a little bit of a peek of what we're looking at in the future. So these are a couple of features that I would classify as possibles or likelies for C# 11. So the first one is stack allocating any array type. So a common pattern that you will kind of see in .NET today is this idea of like, I'm going to process some data here. I have a span of bytes or some input form. And if the argument count is below a certain threshold, then I'm going to stack allocate some data. Otherwise, I'm going to allocate an array because we don't want to, if you don't want to just blindly stack alloc because you might end up blowing the stack if someone gives you too much data. Like I said, this is a very common pattern in .NET. It works fantastic. It's a great trade-off between kind of performance and productivity. The problem is, what happens when you start using a span of anything that contains a reference? Like if you just have a span of objects. Well, the exact same code doesn't work because you can't stack alloc arrays of types which have managed references. And so this kind of it's really disjoint. It really hurts your ability to take something you know and apply it to all these different scenarios. And people end up doing these really awesome or ugly tricks, depending on how you look at it, to get around this. They will, for instance, take a struct, they'll put a whole bunch of objects in a row, and then they'll do memory marshal, create span across it, because that creates a span of objects, and it functions. It's very unsafe. This span is not lifetime tracked, and so you can very easily corrupt memory by returning it. And so it's basically an unsafe method that works, but it's also awkward. You have to learn special techniques, and people end up not wanting to do this and sacrificing performance because it's so awkward to do. But what we're going to do in C# 11 is we're going to try and fix that and make it so you can just write that code exactly the way you wanted to write it. You can take that knowledge you already had on how to deal with kind of stack alloc versus array allocations and apply it to any type in the framework. The next thing we're looking at is param span of t. So today with .NET, the only kind of variable argument passing we support is params arrays. And so we have like an example here. We have a pin line with a format and a params object array. And you'll see it's like the very simple use cases of a pin line passing first name, last name, and address. Under the hood, though, the code we generate leaves a bit to be desired. First off, we're using heap allocated arrays for argument passing. That's unfortunate. But even worse, these arrays are not consumed by a pin line. Like the caller does not store these arrays. They just process them and return. Yet we have to allocate. Yet because of the way C# works, we can't know that. And so we have to assume that those arrays are stored. And so every time we have to allocate a new array. We can't do any kind of amortized allocation here. And as a result, this ends up becoming a bit of a problem for people, again, in high performance scenarios. And library authors tend to compensate by adding overloads where they have like take one object or take two objects so that they can avoid that array allocation in kind of the common cases. And that works, again, it's functional, but it really devalues params as a feature because we're, again, saying, yes, this is productive, but in high performance scenarios, you might want to think about not using it or think about the implications of it. Well, in C# 11, we want to do read-only span with params. And that is advantageous because with spans, we understand the lifetime. It's a ref struct and we can track it. We can know whether or not it's potentially consumed by calling code. And as a result, immediately we can amortize that array allocation. We can allocate an array one time, convert it to a span, pass it for the first call, then reuse it for the second call and just do a correct slicing on the way in. Even better, if you think about that a feature I just showed you a second ago, we can get rid of the heap allocation entirely. Just stack alloc into this span and have no heap implications for passing this along. Even better, if you go back to the first example, we're designing it so that it will retrofit into existing APIs nicely. You can add this append line with params span of t overload, and the compiler will just prefer that over params object when present. So once again, you can retrofit existing code, customers update, they don't change a thing, and performance gets better. Those are always like fun features for us. Lastly, we're looking at ref fields. Now, if anyone's ever looked at like span of t and they've asked like, well, what is span of t? Like, what is the secret sauce? We've always kind of told them, oh, it's a tuple of a ref t pointer and an int length. The problem is that we were kind of lying a little bit. Like if you ever went and looked at the source code for span of t, you found it was actually using this type called by reference of t. And what that is essentially a ref field. It's a type that is kind of like a ref field that is understood by the CLR, but it is not understood by the C# compiler. So all uses of this type are incredibly unsafe. It is basically a pointer which will hold memory if it points to a reference type. And this has a couple of downsides. One is that it makes the .NET code, the .NET platform less safe because our core type, we essentially have some unsafe code and we have to be very careful in how we use this and manage this. Secondly, it means that that secret sauce behind the success of span of t, other customers can't build that same primitive. Like we've had other customers come to us with very compelling scenarios on, hey, we want to create something a lot like span for like these particular domains that we exist in. Can you give us ref fields? I'm like, well, we can't give you by reference to t. It's extremely unsafe. But, and so it kind of limits that secret sauce to the runtime. Well, what we want to do is just simply fix that. And we want to make it so that we have ref fields as a general supported feature, and we can delete by reference from our framework and just make span of t the type we always told you it was. Now, looking beyond C# 11, there's a couple of other items that we're kind of looking into as potential features. The first is having ref structs as generic arguments. So today, ref structs, much like pointers, cannot be used as generic arguments and methods. And that is merely, there's nothing fundamental stopping us. We just haven't ever been compelled to do the work. But we're starting to get to a point where we want to allow it. It's becoming enough of a blocker that we're interested in moving forward with it. And we imagine it'll be some syntax like where t ref struct. It looks like a constraint, but it's really kind of an anti-constraint. And that would allow us to pass ref structs like data into the process method, which if you kind of think under the hood, that's actually creating like a span of a ref struct. And that's kind of an implication, is if we allow this, we can have span of spans with this type, and it will work just fine, and it will fall out from the design. And this is advantageous because there's a lot of places in the runtime where we have an algorithm that works for, generic types, and then we have to have an overload for every ref struct that we have, because we can't special on ref structs, even though the algorithm is completely safe for the ref structs. And lastly, in kind of the similar vein of places where we have kind of interfaces that represent behavior, we can't apply them to ref structs today. And we're looking at changing that and doing the work in the language to allow ref structs to implement interfaces. And once again, make it so that we can start sharing that code between all the types that should be shared, and not having to bifurcate our code based on ref and non-ref structs. All right, so that's the end of my talk. I do want to say a big thanks to Stephen Tobe, Tanner Gooding, and Aaron Robinson. They helped me out a lot with some of the details of this talk. They own a lot of the parts of the runtime that took advantage of these features. Very helpful. My contact information is here, and I think we're at a Q&A section.
Yes, so we have a few questions.
A few?
Loads of them, but let me start with some of them. So there was a long debate about how many features are being added to the language right now, and what's your perception and the team perception behind the growth or the expansion of the language in various directions. I won't quote a specific question because there were several ones mentioning the same, but it would be nice to hear your opinion.
I think it depends on, so you can look at some features as, you kind of have to divide the world into a couple different ones. Like, is this feature adding a new concept, or is it removing kind of a blocker in an existing concept? Like, I would argue that like ref returns in some ways is not a new concept. We had ref parameters, and ref returns are always kind of there. We were just removing, like if you kind of dot out a matrix, it's like, well, I can have a ref parameter, I can have a ref return and ref local. It's more taking an existing feature and expanding it to have a more complete implementation and removing a friction point. And well as when you look at like some of the stuff I point out for C# 10 and 11, the idea of stack allocating object arrays over int arrays, that's just removing a friction point in a somewhat arbitrary limitation. I mean, arbitrary, based on resourcing, and the idea of implementing interfaces on ref structs and allowing them as generic arguments. Again, these are all just removing limitations. Yes, they're features, but it's removing friction points and kind of making the language more complete and, I'm missing the word, more regular. It's making the language more regular. Now, there are other features we add, but, and in terms of expansion, I gotta say, like I do understand that from the outside, like we are starting to move faster. We are releasing every year now. We are keeping up with the .NET framework train. But a lot of these features, like we are adding them, features really only get added to the language when there is pretty much an extreme need. I mean, we say, like when people want to join my team and they're like, hey, I want to like join the C# compiler team. One of the questions I asked them was like, how good are you at saying no? Like, how good are you telling people no? Because we have to say that a lot in the compiler, because people have a lot of ideas on what to do with the language, and some of them are very good, but they don't stack up against all these other asks that we have. And so the asks that we get here when we do these like features, it's because like there's a huge demand and they fill a huge need, and that's why we end up doing them. And so yeah, the language is moving faster than it used to, but it's because we've actually have a better release vehicle now with .NET Core, where we can release more often and provide value. And we have a lot of demand for getting things out there to help unblock a lot of scenarios.
Awesome. I think this answers the question. There was a huge thing about the regex stuff. So that was like some of the responses that it's wild, and you had me at debugging through regex. So a lot of good stuff related to this. Also, think like a more generic question about your favorite books, videos, methods, blogs, anything you can learn from, or particularly how you learn from.
So I was actually very fortunate. I started using .NET at like 1.0, and so I got to read Jeffrey Richter's like original book. I think the book is now called, I believe, CLR via C#. It's still a very good book, but I read it like way back in the day. My overall favorite books, though, are pragmatic programmer. That is very much encapsulates like how I think about code. It's just pragmatic choices and immutable data structures. The immutable data structure book, like, probably more fundamentally changed how I thought about programming than any other book that I read besides Pragmatic Programmer. Like those two, it's just like, oh, this was early. I did not, in college, I did not have a functional upbringing, and I did not get a functional introduction until I was in my professional life. And that was kind of a book that really kind of like turned me on my head and said, oh, that's a really interesting way to think about programming. So that is my favorite one. In terms of blogs, I don't read as many. I get most of my content from Twitter and find blogs from there now. I used to love reading Raymond Chen's blog and Eric Lippert's blog. Even when I worked with Eric Lippert, I'd be poking him like, when are you going to blog about that? So I can go like read your like in-depth thoughts about it.
Awesome. Yeah, I think this answers the question. There was one about the interpolation and resource files.
Don't quite. Will interpolation work in resource files? I believe we would have to change the code generator to make that work. That would be more, I think, of a change to the resource file tools than the language, because those files, I believe, they just get the XML and just generate the code straight out, and they would have to change that entire tool chain there. I don't think there's anything stopping them other than it would involve them to iterate a bit on the resource file format as well as some of their like XML formats.
Okay, all righty. I just scanned through the rest, and we are a bit closing. We are quite close to the next session provided by David Fowler. So I think we'll be wrapping up right now.
Great.
And thank you again for providing us with all the knowledge. And I think that we'll have some conversation inside Dotnetos as well, with the span of objects being allocated on top of the stack. That was a really, really interesting one. So thank you again for being with us, for presenting, and have a good day then.
All right. Thanks so much, everyone, for coming and listening. You all have a great day too.
Take care. Bye-bye.
Bye.